Welcome, and thank you for joining us for this ABB webinar supported by Data Centres Ireland. My name is Kirsten Hill, and I am the Event Manager for Data Centres Ireland. This webinar will be presented by Frank Grundholm, Vice President, Global HVACR Sales at ABB Motion. The presentation is called Specifying Variable Speed Technology for Data Centre Cooling. Please visit the Data Centres Ireland website to view other on-demand content, as well as the latest information on the Data Centres Ireland Virtual Festival, which will be taking place on the 16th to the 20th of November 2020. If you would like to ask any questions during the webinar, please put these in the chat box. This webinar will be recorded and uploaded to the Data Centres Ireland website. And now, over to Frank.
Thank you very much, Kirsten, and thank you to everyone for joining. I'm very happy to be here today to talk to you a little bit about the specification of data center cooling technology, and especially in particular the variable speed technology and both the positive and negative impacts of variable speed technologies, so that you can work with your data centers in a more efficient way and avoid any pitfalls from putting forward the right specifications. ABB is a global company with about 110,000 people across the globe. So we are represented in virtually every country in the world, most of the countries directly, but a few countries only through partners, with a range of products ranging from industrial to infrastructure to buildings, so robots, but mostly electrical products, if you will, including, of course, motors and robots in that area, as well as EV charging stuff. So if we look at the energy uses of data centers, about 20,000 terawatt hours is used annually by data centers. That's about 1% of the world's energy produced, and it's increasing. So managing data center energy consumption is important not only for the individual data center, but also for the environmental impact of energy production as the percentage increases. Its annual consumption growth is about 1 to 2%. Now, that doesn't sound like much, especially, considering the situation we're in right now with the pandemic, everybody's working from home. You would expect a massive explosion of data center development, and there are more data centers being built. But all data centers are also becoming more energy efficient, but not just on the cooling side, but also on the server side. Density is higher, actual available data power, if you will, for the same kilowatt hours is increasing. 2/5 of the energy consumed, however, in a data center is for the data center cooling. So managing the energy for that part of the data centers is almost as important as managing the energy consumption in the data part itself. And if you look at the opportunities for savings, then 20 to 60% of the energy can actually be saved by applying variable speed technology in an intelligent way. And I'll go through this in my presentation. So a lot of people, they perceive data centers as fixed loads. For a lot of people, it's like, well, we consume data all the time, but there is actually variability over the day. Everybody knows we don't consume data at night, but then the assumption is, well, then they just consume it in the US. But different continents are served by different data centers. So largely a data center follows the region pattern. So as activity goes down during the evening and nighttime, so does the data center load. And that means that you have variability, and you need to manage your efficiency of the data center based on the part load, because most of the time you're operating at 80% load or less, and quite often down to maybe 10, 15% load. And that requires the ability to scale the loads but maintain efficiencies. Now, if we look at just the motor technologies applied, then IE4 to IE5 motors bring 5 to 15% energy savings compared to IE2 and IE3 motors. But when you look at where the real saving potential is, even though those percentages are there also in the full load, as you look at the part load curves, the gaps actually increase. And that's where you have the biggest potential for real savings is in the part load condition. Now, if you look at EC motors, for instance, which have become very popular in the fan side especially, then they are typically around IE4, where most induction motors today are available in IE3. So there is a good saving with an EC fan motor. But specifying, flat speccing a motor technology is dangerous because we've seen specifications insisting on EC motor technology. But since that specification was written, new technology has come into the market. Today you can get, for instance, synchronous reluctance motors with ferrite assist, which is a hybrid between a magnet-free motor and small permanent magnets, but made from ferrite, which means you don't have the sustainability issue of neodyne magnets and the mining around that. But they are actually in IE5. So even compared to the high-efficient IE4 motors, you still have, especially in the part load conditions, a high potential energy saving by allowing newer technologies in your applications. So it's important not to specify the technology, but to specify the requirement being the highest possible efficiency, or, if you will, the lowest possible energy consumption. Now, unit size is one of the driving factors for the specification of EC fans as well. But when you look at it, EC fan design only affects essentially the length of the unit itself. It doesn't necessarily affect the length of the installation, because you still need to have a reasonably laminar airflow to avoid excessive pressure increases in your ducting, for instance. You need to manage your airflow so that you don't create these hard bends after the units. If you compact your mechanical room too much, you get hard bends right in front and behind the units, and that then increases the pressure drops, and thereby you get plenum issues with turbulence, and that increases your pressure drops internally and thereby reduces the actual unit efficiency. So even though in test conditions the unit might be efficient, if you install it wrongly, you lose that efficiency. And again, we have to remember 99% of the time, units run at 80% load or less. Now that also means that 1% of the time we're actually at peak load. So specifying for peak load doesn't make a lot of sense. The opportunity we have if we apply variable frequency drives is that we can look at overspeeding the application. If we overspeed a fan, there are some penalties for that. Energy consumption at the full speed, which will then be maybe 60 or 65 hertz, actually increases. Now, that's of course a problem, but it's 1% of the time, and it would allow us to possibly use the fan at a better efficiency point through the majority of the load cycle, and thereby the total efficiency of the system. Even though we get a penalty on the high speed side, the total energy consumption over the duration actually decreases. Then there's the penalty of noise. Noise on a fan is a logarithmic function. So you will have a massive increase potentially of the fan on the peak load. But again, if it ever happens, it's a maximum of 1% of the time. And when it will happen is typically in the middle of the day, where you have a lot of ambient noise. You've got trucks on the motorways. You've got a lot of people running around. You've got a lot of other installations making a lot of noise. So the impact of increasing noise in the middle of the day on the surroundings is not as significant. If it had been in the nighttime, I would never recommend overspeeding. In the nighttime, you have zero noise in the city. Well, not zero, it's never zero in the city, but it's much lower in the nighttime. And we've seen instances where fans running at full speed, just nominal full speed in a city on a rooftop unit, caused issues for the neighbors, so much so that they forced interruption of operation during the nighttime so that they were able to sleep. But during normal operation, you run at a better efficiency point. And by doing that, you also improve the total efficiency of your system. And EC fans, for instance, cannot be overspeeded. But what happens when you can overspeed is you can also use a smaller unit. It's shorter as well, but it's also slimmer and not as tall, which means on those parameters, you can actually optimize your utilization of the mechanical room. Drives, they save energy by controlling the motor speed of the fans, the pumps, and the compressors. But there is a penalty. All rectifier loads generate electrical noise. So while the motor may result in current waveform distortion, that is called harmonics, there are ways to manage that. But excessive harmonics in a system can cause issues with system reliability, with energy efficiency of the system, because you get heat losses on your cables, your fuses, your disconnects, all your electrical switchgear is increasing in heating. I'm hearing a lot from installers that the cable quality has decreased because they're seeing that cables get warmer. It's actually not the cable quality that's the issue. The issue is that when I started in the business back in 95, we had maybe 10-15% rectifier load in the building. Today we have 99% rectifier load in a building, and all of them have some level of harmonics disturbance. So the heating caused by rectifier loads has increased dramatically and is on every single cable. And that means we're seeing hotter cables, we're seeing potential risks with insulation failures, because the insulation on the cables actually hardens when it's exposed to too hot conditions, which then again can potentially cause a fire hazard if it cracks. So we really need to manage this to the right levels. We need to make sure that we either dimension with larger cables, or we manage the harmonics so we don't have to over-dimension our cables and electrical switchgear. Now, what is the actual impact? Well, it's a simple equation. So we usually look at the heating in a cable based on the active current and the resistance in the cable. And that gives us sort of the power that would sort of give us an indication of what the heating is. But when we have harmonics, we have currents at different frequencies, which are additional to the fundamental. And then the current we have to use is the RMS current, so the root mean squared of the fundamental plus the harmonic currents multiplied by the fundamental current. So this means that when we look at the Joule losses in conductors, if we have 40% THDI, which is quite common in a standard drive with DC chokes or AC chokes, or even some of the best EC fans will have around 40% THDI, the energy losses additional in the cables are actually 16%. So just because we use a rectifier load, we've now increased the heat losses in the cable by 16%, which means we have to overrate the cables 16% relative to the active current that we have in the system. If we make a comparison as to what options do we have? Well, I said 40% THDI. So that's actually the solution you have in the middle, where you have a standard DC drive with a DC choke, a true power factor of 0.98, and an active line current around 108% equivalent. If you look at a 6-pulse drive, a standard drive without any mitigation, or some of the standard EC fan solutions, the true power factor drops to 0.78, but the line current equivalent increases from 108 to 128%, which means, again, you have to over-dimension your cables a lot more. If you look at the active front-end drives that are also available, then your true power factor suddenly is unity. You don't have line current issues with harmonics. The harmonic THDI, so the current distortion, is 3%, which in rounded numbers equates to a calculation that shows 99.998%, so 100% line current for dimensioning. So in that sense, you have technologies. It is more expensive, but you can gain the savings on your installation, your contactors, your fuses, generators, transformers. But you need to look at, in order to balance the cost of a data center in the right way and avoid operational issues, you need to look at the total cost of that system. PUE is generally the factor that is used for data center efficiency. It's the total load divided by the IT load. The IT load essentially being the total minus the cooling load. Now, with that, we get a PUE, and the closer it is to 1, the more efficient the data center is. However, what that doesn't take into account is the actual inefficiencies and losses that we could have through harmonics. Not only can it cause operational issues in the plant, but it also has an energy efficiency impact that is indirect. So we get potentially kVAR charges or non-wattage charges from our utility for bad energy performance. There are standards for how to design a data center. These standards, however, quite often don't encompass all of the details. They are very generic in use. So I'm just going to take the one that would theoretically deal with power, and that's the -2-2, power supply and distribution. Now, if we take a look at that, it just says that the low power factor and harmonics shall remain within the boundaries on any contract from the supply utility. That doesn't really help in terms of securing operational resilience of the data center. It then also talks about critical loads, but the cooling system is not perceived a critical load. But the cooling system is a large part of the total power consumption, and thereby any distortion in the cooling system on the power quality will have a negative impact on the data servers, the UPSs, the DC supplies. So the distinction between critical and non-critical in the terms of harmonic management is actually not a very good distinction to make. Improving power factor is often done with different external solutions. So we can add an active filter. There can also be passive filters added. And they manage, but they spot manage. And they don't necessarily manage the full system. And we don't want to have the system run into problems. So I'm going to show a slide that sort of give you an idea about where is the real impact of this. So first of all, you can get drives and these pulsations. If you do measurements, you will see these kinds of pulses. If you have the bunny ears, then depending on how deep it is, that gives you an indication how good is the passive filtration that you have in your system. With a good input reactor, it sits relatively high. You can also have multi-pulse drives with passive filters that smooths it a little more, or multi-pulse drives for the larger units, but it requires an expensive transformer. But when you go to the active front end, you can see you have much more resembling a pure sine wave. So there are different technologies, and it's a matter of making the right choices, and it is complex. Ask the manufacturers to make the necessary simulations for any variable speed. Any variable speed solution produces harmonics, and you have to request that from all types of variable speed equipment. You have to make sure that the specifications applied are actually pulled out across not just the variable frequency drives, but any variable speed unit supplied. An active solution, it looks complex. It's got big filters. It's got 2 sets of active units. So one controlling the motor, one controlling the feedback to the supply network. But it is the most optimum way. But what's important to look at is that you actually get the DC bus capacitors. Because with the DC bus capacitors, you also get the ability to actually boost the intermediate voltage inside the unit, which will then, if you have a low input to the drive, you can actually still have full input to your motor. Now, during a brownout, you can potentially provide full power to your application and maintain operation in that instance, and thereby increasing the resilience of the data center. What that means is, when you have a supply voltage of 400 volts, if you add a passive filter, if you add a standard 6-pulse drive, and you have a motor with a 92% efficiency, but your motor voltage is 370 volts, then you get additional heating in the motor, you get additional heat losses in the motor that you need to factor in as well. And the application performance is reduced at the full speed because you don't have the full voltage available. You avoid, with an active front-end solution, you avoid the additional filters. You do have a lower drive efficiency from 98 to 96.5, but your motor efficiency goes up simply because you provide the nominal voltage at the nominal operating point and thereby avoid the overheating. So the same motor now has a higher efficiency. So in total, the actual package is more or less the same. So the whole discussion that active front-end drives have a lower efficiency is true on a unit-to-unit measurement, but on a system-to-system with the same harmonics performance, it's more or less the same. So don't talk about efficiencies on a unit level, talk about system efficiencies and look at what does it actually mean for the whole system. And even ignoring the motor, the 0.5, it's still the same. The main difference is really that you avoid the losses in the passive filter components or external active filters. What you then get additionally, if you have an active filter, the active filter only filters towards the utility, towards the transformer, towards the genset, but not backwards in the system. What this means is you still have the high THDI inside your building, which means you have to dimension fuses, contactors, disconnects, and everything else for that. If you use active front-end drives inside the building, now you can suddenly reduce the dimensioning of your entire operation. So the entire electrical system can be optimized in terms of cost of installation. Oh yeah, another part is with this, you actually have a single point of failure. If one drive fails here, your harmonics don't go up towards the utility because the drive fails and all the other applications will run at the same lower THDI. If the active filter falls out, potentially your transformer will trip on an overload. So that's, again, operational resilience by decentralizing your mitigation. Capital cost, there's a lot of the capital cost that comes from mechanical, of course, instrumentation and shell. But if you look at the fit-up costs and the fees, that's also a substantial part. And 20% of the data center capital cost comes from mechanical and 36% are from electrical. So if you can start managing your 36% cost in a more efficient way by reducing, say, 10, 15%, that's a substantial potential cost saving in your projects. So just an overview of where you could have the savings. Cabling is typically around 10%. Switchgear and breakers, 10 to 30%. Gensets actually have a requirement from most manufacturers that the derating of the genset is about 50% if you use a standard 6-pulse drive. And the standard 6-pulse drive actually also includes EC fans because they are perceived as standard 6-pulse drives towards a genset. If you use an active front-end solution, that derating is avoided. Distribution transformers typically require around 20% oversizing because of harmonics from 6-pulse drives. So these are the types and levels of savings that you can get when you look at your whole project, but you need to look at the whole electrical package when doing so. So no need to oversize. You have continuously clean, disturbance-free network, and you have the resilience that you get by decentralizing. So decentralizing your mitigation is really one of the key benefits when you have critical operations like data centers. And it's more compact. It takes up less space than you would in many other types of solutions. High frequency noise is another thing that you need to take into account. You need to take into account the immunity requirements on the system, and variable speed solutions of any kind, according to EU regulations, has to follow the power drive system standard. So part of the specification must always be the EN 61800-3 adjustable speed electrical power drive systems, EMC requirements. This applies to AC and DC variable speed solutions, and EC motors are BLDC motors, so DC motors with electronic speed control and thereby in scope of the PDS standard. Some use the generic standards, the 61000-6-2 or -3 for EMC, but immunity is not fully covered by those. And especially in critical installations like data centers, make sure that the right standards are applied. One statement from an EC fan manufacturer that I really don't understand is, I'm not supplying drives, I'm supplying fans, and there are no EMC requirements to fans. Make sure there's a clear link between your mechanical specification, where the EC fans are typically part of the package, and your electrical package, where the specification for drives is. It can be a simple statement in the mechanical specification that any variable speed equipment must meet the electrical requirements of the variable frequency drive section of the electrical specification. That way, nobody can make statements like that, because they all connect to the same network and they all have impact on the same equipment when they generate the same kind of noise. So really important that the main difference here is that it's on the immunity. And immunity in a data center is critical for the resilience. If you're not immune to harmonic voltages, well, then there is a risk if there's harmonics generated, and there is. If you're using an active filter at the central point, there are harmonics inside the building. And you should be able to tolerate minimum what is required by the PDS, which is 8% voltage distortion. If you're in data centers in a location where you have voltage variations, commutation notches, then you need to make sure it follows those requirements, because otherwise you risk that the units fail when you have these variations. Again, another reason why the use of 61800-3 is critical. So in summary, I think I've captured that in the last couple of slides. But power quality is an important part of efficiency, and active front-end solutions are a good way of getting there. So I don't know, Kirsten, if we have any questions.
Haven't had any questions come through yet, but I'll wait a little bit and see if any come through.
Yeah, if you have any questions or comments, please put them in the chat, and we're more than happy to answer those. Otherwise, you have on the screen, you have a web page where you can find more information specifically to data center cooling. And we also have, of course, as Kirsten mentioned, the panel discussions at the virtual festival next week.
Amy Duke said, thanks, Frank. Very informative presentation.
Thanks, Amy.
Got someone else typing, so I'll just wait. David Glennon says, hi, Frank. Got a few people typing, so.
Always good to have friends in the audience.
Yeah. So David Glennon has a question. Do EC fans have power ride through and catch on the fly capabilities?
Power ride is typically a challenge in these very compact units, because they don't have the larger capacitors that you would find in a standard variable frequency drive. So the power ride through capability will be less. Also, when you compare to an active front end solution, as you get issues, typically the voltage won't drop off immediately. That's not what happens in most cases. You get a variation where it drops down. And in those situations, active front end can boost the voltage and maintain it at a higher level. So the ride-through capabilities of EC fans are not as good as they are on a VFD. On the catch on the fly, they do have some capability in that regard, but again, they're not regenerative. So they can't necessarily use the power as well from generated by the fans. So it depends a lot on the manufacturer whether or not you have it. Most of the standard drives do have a fairly decent catch on the fly capability. That is, ABB has that, but a lot of other manufacturers have that as well.
Perfect. Paul Boylan, he says, appreciate they take up less space. However, do the low harmonic drives require more or less specific cooling?
There is obviously a little more heating. It comes from the efficiency that you saw. I mean, a standard drive is 98% efficient. An active front-end drive is 96.5% efficient. So yes, there is a little more heat generated because that is what it translates to. That being said, it's not a lot. And if you have a passive solution, there's a heat loss from that as well. That will typically be installed next to the drive. And that has a lower efficiency total for the package than if you use an AFE. If you use a centralized active filter, that has heat losses as well. And in many data centers, that's part of the same electrical room, because a lot of times the drives are pulled into the centralized electrical rooms. The alternative is that you can put out the drives into the applications, and then you can use actually just the airflow, the exhaust air from the data center to cool the drives. That way you're actually just heating more the heat that you're already exhausting from the data center, and you get rid of the heat without putting it into the data center, which could require more cooling. So there are ways of managing that additional heat load intelligently.
Perfect. We've got someone typing, so I'll just wait and see if... Paul says thank you. Just wait and see if anything else comes through. So James Butler says, how interchangeable are spare parts in EC fan systems from one manufacturer to another?
Well, one of the challenges in a data center is when you apply EC fans, you apply them typically in fan walls. Since the fans are in parallel with each other, you need to have identical fans in the entire fan wall. That also means if you have a failure on one fan, the requirement is that you exchange the whole fan unit. You can't leave the fan wheel there. And that means you have to go back to the same manufacturer to get an identical fan when you do the replacement. In a traditional system, you would still be able to have a fan wall design, because a fan wall design does have some benefits. But if you have a failure on the motor bearing, you would exchange just the motor, not the entire unit. So you would leave your fan, you would leave your entire framework, and the drives even. If there's a failure on the drives, you would just exchange the drive and leave everything else behind. So the flexibility of repairing is higher when you have modular systems that you would have with that, and you don't have single source for your spare parts. EC fans, at least from most manufacturers, cannot be repaired on site, and that is one of the challenges. You have to exchange a whole unit every time.
Perfect. We've got someone typing, so we'll just wait and see.
Yep.
James said thank you for that answer. Wait a few more seconds, see if we get any more. Stephen Corley says, is there efficiencies comparisons on EC fans packages versus VSD/IM installs? Take an ULH or 6-pulse for discussion purposes.
We have some. It's not publicly available, but on request we can certainly show some of the data that we have from our laboratories. I prefer only to have public data when it's done by third party. So our internal lab testing is we maintain internally and only share on specific requests.
Perfect. Jogendra says, how is the synchronization done?
Synchronization. So not sure what the question is. Jogendra, if you could add just a little more comment to that. Synchronization on the motor side or on the main side? Because on the motor side, I mean, it's looking at the frequency or the rotation speed on the motor based on inducing currents. And that's how all the manufacturers do it. Some just are faster in their processing than others. On the main side, there is no synchronization in that sense, because when it's not unless it's a regenerative drive, which in a data center it rarely would be. Okay, on the motor side, yes, that is when a motor rotates and you induce a current, you can actually measure the frequency of rotation. And then you use that to capture the motor by setting the same rotation, the same frequency on the output of the drive as you actually measure in the motor. And that's how you manage that. On very long motor cables, there can be a challenge sometimes, but generally it's accurate enough that you avoid the peak. If you just capture a motor that's rotating without adjusting the output, you'll get a very high peak and the drive will trip out. And that's why catch on the fly is a critical feature to avoid tripping of the units.
Perfect. Well, I think that might be all of the questions for today. We haven't had any more come through.
All right.
Perfect. Well, thank you very much, Frank. That was very informative.
Yeah, and thanks to everyone again for joining. Hope to see you out there.
Perfect. Thank you.